I run or organize the Bay Area Hackers Association, as far as associated hackers can be organized. And so we meet once a month. And so if you're in the area or you just want to join our list, that's cool. You don't actually have to attend the meeting in order to join the list. So, why study failure? Well, David Kahn's pretty famous for saying that few false ideas have more firmly gripped the minds of so many intelligent men that than the one that, if they just tried, they could invent a cipher that no one could break. Also, to learn from history, right? We've got to learn from history in order to prevent making the same mistakes. But nobody really knows how to make unbreakable crypto, with potentially the caveat of one-time pads. So we have to learn how to make things that aren't breakable by any known technique, and then sort of hope for the best. So we need crypto in web applications in hidden fields. We need them in get parameters. We need them in post parameters. We need them in cookies, especially authenticators that we're going to spend a lot of time talking about. And anything that gets sent to the client and intended to return unaltered, right? We're storing on the client side, so we have an untrusted storage device. And so oftentimes we use crypto to prevent tampering, but it's usually done in the wrong way. And I'm going to tell you about that in a second. Usually, an authenticator is just the blanket name I give to anything that indicates that the user's gone through the login process. It's used generally instead of HTTP auth. It could be a session, could be a cookie, blah, blah, blah. It doesn't really matter. As if it goes to the client side and it comes back and that tells the system that you're authenticated, then it's an authenticator. It usually implies or includes the login name. It can't be stored in plain text, so typically it's encrypted. But with encryption, you're normally sending through the internet, the untrusted medium, to the recipient, right? And when you have a large number of sender and recipient pairs, you tend to use public key crypto in order to reduce the key management. That's really the only reason to use public key crypto is for key management. So if you don't have a large number of sender-recipient pairs, you're better off with symmetric. But what we have is something a little bit different. We have a website that sends data to the browser and just wants to get that same data back, okay? So we don't have a separate sender and recipient. Now, a few other mistakes that are, and we're going to talk about what you should be doing instead of encrypting in a second, but a few other mistakes that people have made. Back in the day, so this is the Wall Street Journal, actually. They didn't really realize that crypt is not an encryption routine. It's a library function that was used for hashing system passwords. It's really close to DES encryption of plain text of all zeros, using the input as the key rather than as the plain text, right? So those inputs are reversed from normal encryption for the way you use most ciphers. And it depends on being able to unable to determine the key given the ciphertext. Now, this was invented prior to secure hashes of any kind, prior to even MD5. And then they made DES slightly different. They added 12 bits of salt to perturb the encryption mechanism so that off-the-shelf DES hardware implementations couldn't be used to brute force it faster. They were also designed to, well, okay, so the salt should be random, and a nice side effect of this is that identical passwords didn't hash to identical values, assuming they had a different salt. And then the salt and final ciphertext are encoded in a printable string in base 64. But Unix crypt is even a little bit worse than that. The user's password was truncated 8 characters in original implementations. And those are coerced down to 7 bits each, because DES uses 56-bit keys, right? We're using the password as the key. So that forms the 56-bit DES key, and it actually dumps, I believe, the least significant bit. So in addition to it being ASCII, so the high bit's probably 0, now you've got the low bit forced to 0 as well. The salt's then used to make part of the encryption routine different, and then it's used to encrypt an all-0 block. And you iterate that 24 more times, each time encrypting the results from the previous round. That was designed to make it take about 1 second on the hardware at the time in 76, 79, whenever they implemented this. So here's the Wall Street Journal's .com's Flaw. Their first mistake, our first of the talk. And so basically, if plus is concatenation, they basically did a Unix script of the salt with then the username concatenated with a secret string. And that would give them encrypted data, and they use that as the authenticator. Does anyone see the problem with this particular one? Okay, so the hint is, where's the secret string located? The secret string is after the username, and I just told you that it takes, it only accepts 8 characters, that it truncates after 8 characters. So it's only hashing 8 octets. So as long as you have a password that's 8 characters or more, the secret word isn't even involved. So what you could do is you could pick an 8-character username. Oh, I guess they base this on the username. You pick an 8-character username, you pick a salt, you do the crypt yourself, and now you have a valid authenticator to the wallstreetjournal.com without even knowing the secret string, right? So crypt is an encryption routine. I'm sorry, that's a failure, and it says when your best isn't good enough. It was the wrong tool for the job. Now, the second flaw is that they had usernames identical in the first 8 letters had identical authenticators. Thus, the interrogative adversary, someone who can just interrogate your website and has no special privileges other than that, can observe that the salt was a fixed constant in the program. All you have to do is register 2 names with 8 characters, and then you can see that the authenticator you're getting back is the same. So the salt is fixed. And that means I can use one authenticator with another user's login, assuming both of them start with the same 8 characters. So yeah, I don't even know what they were doing there. That's a little bit bizarre. Hard-coded salt, bad idea. So the third one is that we would, so this one allows you to actually recover the secret string. And this is a pretty cool attack. And it actually dates back to the 70s with the 10x system. In a slightly different form, we see this all the time. We actually saw it more recently in the PKCS padding Oracle attack. And it's the adaptive chosen message attack. And in this case, you register a 7-character username, like failfay, and then you compute the crypt, and you basically try the first letter of the secret string, and you try each one until you get a valid authenticator. And then you do the same thing with the 6-character username, and you can break the authenticator 1 byte at a time instead of having to guess it all at once. So this is basically exactly the same attack that was used in the 10x password recovery back in the 70s. It's the same attack that's used in the Netafera's Poet, padding Oracle something attack. And by doing this, the adaptive chosen message attack, you can break this in 128 times 8 iterations instead of 128 to the 8th power. So each query taking 1 second. The secret string was March 20. Not sure what that means. Maybe the date they launched their website. But we got it in 17 minutes instead of 2 times 10 to the 9th years. Right? Big deal. So that's sort of an epic fail. I don't know. 17 minutes to recover the secret. Okay. So bad crypto generally, we're going to see the same things happening over and over again. Number one, the best crypto can't save you from a broken RNG. It's sort of the random number generation is the sine qua non of crypto. You can't do anything else if you can't throw dice where your opponents can't see it. And this happened in the Netscape SSL. This has happened with, to a certain extent, with mscrypt.genrandom. There are problems with dual EC DRBG, and then most lately with Debian OpenSSL. And so, and also, I don't know if anyone else has noticed, seeding is a real problem in these high-level frameworks like Java, where it just assumes that you're going to get the seed value from somewhere, but most developers don't even bother, right? So it just defaults with the current time or something along those lines. So even though you have this great computationally strong random number generator, you're seeding it with the current time. In Debian OpenSSL seeded it with the process ID. That's not all that different. So hashes generally. Cryptographic hashes are one-way functions. Given an input, it's easy to compute an output. Given an output, it's difficult to compute the input. A tiny change in the input also generates a big change in the output. On average, half the bits change. So, so one of the main mistakes that people make is hashing with no salt. So you're allowing a user to pick a secret S, their password, for example. It's easy to guess. You don't want to store it in the plain text form. You pass it through a hash instead, and you store the digest. I assume that most people know what the problems are with these days. with us these days because of the LinkedIn and Yahoo stuff. But all you do is hash all the likely secrets in a dictionary attack, and it's actually done in rainbow tables that you can download occasionally. It actually is a little bit harder to find rainbow tables than most people make it sound, or at least to get full downloads of them. Seems that nobody wants to dedicate like 80 gigabytes on their seed box just for other people to get more rainbow tables. Not exactly as popular as the latest movie, perhaps. So, rainbow tables are kind of interesting in that they're essentially a clever way to store pre-computed hashes. Like, somebody has to do all the work. And they could just put it in a big file and archive and compress it. But this is actually a little bit more clever in that they use these different functions, the R1, R2, R3 there, to basically transform the output back to the input domain. So that what you might do is for a given hash, you would try a different series of R1, R2, R3, and then see if the final value, the one in the rightmost column in this screen, is stored in your database, and from there you can figure out what the original input was. It's kind of a time-space trade-off. It just requires you to do a little bit more time to look up the data because you're actually having to perform some computations, but it's clever. So now that's not the only threat that we're really facing here. Whenever you're hashing weak or easy-to-guess secrets, I suggest that you prepend sort of a unique random byte series to the secret, sort of a salt. I recommend as many bits of salt as your hash has output. And if you're doing it with hex-encoded characters or something, then obviously double it. That guarantees that the rainbow tables would have to hash every input, not just the likely inputs. So better than that, you can do HMAC, which you're going to have to do some key management in this case. But instead of a simple hash, it's basically like a keyed set hash. We'll talk about that later. Or for passwords in particular, PBKDF2 or scrypt, or maybe even bcrypt are good options. Now, these just make it more difficult for the attacker to attempt various hashes. You're still on an even playing field, which is kind of unfortunate. But in any case, those avoid the problems of key management. So going on to ECB mode, electronic codebook mode is basically the way that you would assume that ciphers were used if you had never studied cryptography. You're just going to take independent plain text. You break your stuff into chunks. You encrypt each chunk independently, and that's it, right? But this is vulnerable to a number of attacks, and some of them are very low tech. Some of them are surprisingly low tech. Like, without knowing the key, I can just swap the ciphertext blocks around. Even if it's base 64 encoded, I could debase 64 encoded. I could swap them around. And maybe one of them is, maybe the green is the source account number and the red is the destination account number, right? So now I've reversed a transaction, perhaps. And that doesn't break the crypto. Second, the one that most people talk about, the reason for chained modes, is that any plaintext block that repeats later in the stream will show as a repetition in the ciphertext. So the blocks above show this sort of macroscopic pattern of A, B, 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 A, A, C, A. And so with using electronic codebook mode, if these are like sectors on your disk, what do you think is the most common sector on your disk? It's probably a sector full of zeros, right? And so that's another weakness, is we can still find these patterns at the macroscopic level, above the block level, in your plaintext. And why is this important? Well, this is why it's important. If your plaintext is on the left, electronic codebook mode, you can still see that that's tux. And so all the other modes, the chained modes, fix this problem, and that's what them on the far right. So this is not just trivial. So it still looks like tux to me, it's still recognizable. So that's sort of a fail. So then another one that probably the most popular mode is cipher block chaining. And this is the one that's used in SSL. This is the one that's used in PGP. Basically, the only real problem with it is that it's vulnerable to the beast attack. So if an adversary can control stuff and like observe the ciphertext in real time, then maybe this is a problem. So basically, in this case, the output of the block cipher function, wish I had my laser pointer here, is XORed with the next plaintext block. And the first plaintext block is XORed with something called an initialization vector. This gets the whole thing bootstrapped. And that also makes each ciphertext unique. So if I have two of the same messages, right, they don't encrypt to the same thing. But typically, generating random IVs is too much difficulty for developers, so they tend to use the same key for every user. And in fact, I even made this mistake once, like probably 15 years ago in C. I was writing it, and I failed to initialize a data structure properly, and so I ended up using an IV of all zeros or something. So it can happen even when you think you know what you're doing. In any case, this means that 2 of the 3 inputs are identical, and so that identical plaintext encrypt to identical ciphertext. And so if you're encrypting a password database, this is an obvious problem here. You know, users could see that they had the same password as somebody else, perhaps. Particularly if the database was readable, yeah? Uh-huh. It is basically the generalization of a salt. So generally speaking, it doesn't have to be kept secret. Oftentimes, it's prepended to the ciphertext stream or in the clear in some way. Some of them require you to, some of the block cipher modes, not CBC, require you to keep them secret, I think. But CBC definitely doesn't. CBC only asks that you not use the same one twice with the same key. So the problem that we're seeing that I see most of the time in web apps is that people who think of crypto think of encryption. And your session IDs probably don't need to be confidential. Like, they're just random numbers, right? They probably do need to be returned unmodified. And they do need to be unforgeable. Someone can't just make them out of whole cloth, right? So your authenticator or your session ID, it seems that encryption is almost always the wrong algorithm for this. And so, so the problem with no integrity protection is that if you're fiddling with the ciphertext, it corrupts at least one block. And it's usually the next block. So, but if you're lucky, let's just say that you're fiddling with the first ciphertext block and it ends up corrupting blocks 2 or 3 or more. If you're lucky, that randomly corrupted block will yield a syntactically invalid string. Like, some parser will go, "Oh, this isn't right," and it'll like cause the code to bomb out. Do you log that? Did your developer realize that that's the sign of an attack? Probably not. So it'll be some obscure error somewhere that'll probably never be analyzed in any significant way unless there's a breach based on it. So I don't really believe in luck, right? I believe in cause and effect. So no integrity protection is a massive fail. It's an epic fail. What we really need are something called message authentication codes. Sorry. What we want is a way to verify that data hasn't been tampered with. A hash isn't enough. Someone could tamper with it and recompute the hash. We need something like a keyed hash. And cryptographers spent like a long time trying to do this right. It actually turns out to be particularly hard. Here's how are we doing on time? Okay. So basically, one is you encrypt the whole message, and then the hash is the last encrypted block, and you encrypt it once more for good measure. It's specified in all these sort of it's specified in all these things. Now, there's a problem with using the last ciphertext for your message authentication code, and that is that in the general case where I'm trying to authenticate something to a second party, the recipient has to know the key. And then you can decrypt the MAC with the key, and the block ciphers are reversible, so you can compute other things that would have the same authentication code. This isn't really that big of a deal if you're a sender and recipient, but it is kind of, as a message authentication code, it's an undesirable trait. So that's kind of a fail. That has no pre-image resistance. Second, there is the do the same thing in forward order, and then do it in reverse order. There's some vulnerability that I didn't really have time to like figure out exactly what it was, but it appears to suffer from some of the same problems. Okay, and then people were like, well, let's use hash functions, right? They're one way. So we don't want these pre-image problems. So Alice and Bob share a key K. Alice wants to send Bob a MAC for this. So she hashes together the key and the message. And what's wrong with this method? It should look a little bit familiar. Well, it turns out that this is an interesting attack that I'm going to have to explain just a little bit about iterative hash functions. Basically what they do is they define this compression function here in green, and then they take the message blocks one by one and crunch them through it. And they usually have a fixed initialization vector, like MD5 has a constant IV, believe it or not. And it crunches each of these the same way you might do a cipher block chaining or something. And at the very end, what you're left with is the hash. And bet you didn't know that. And then, assuming that the secret's one block and the message is one or more blocks, there's sort of this flaw, right? And the flaw is, it's called the length extension attack. And what you can do is you just you take the previous hash and you use that as the input to the compression function, and you add on some more data, and you get a new message authentication code. So now I've tacked on maybe some zeros onto the amount that you're transferring into my account. And it's still authorized, and I never needed to know the actual secret, because that's in the first block. So some smart cryptographers said, well, we're going to strengthen these, right? We're going to add length padding at the end. So there's some fancy padding techniques, but it basically has like a bit representation of how many bits were in the original message. And that's going to solve these length extension attacks. But it doesn't really solve them, actually. I pointed this out in early 2009, and then Netafera found this in the Flickr API in September. So what's happening here is there is length padding, and then you add some more data, and you add a new length padding, right? So that's a pretty straightforward attack against this. Once again, I don't need to know the key that's used for this hash function, the secret data that's up front in first block. So a bunch of people have tried various other iterations to try and address these. It feels like we're kind of going down a rabbit hole here. Some people prepend the message length. Bart Prenell is pretty suspicious of that. You can put the secret key at the end of the hash, but collisions in the hash make the MAC malleable, and we don't like that. You could put the key in front and back, or you could put two different keys, one in front, one in back. These are all kind of makes everyone uncomfortable. So many have tried. A few have won. Now, other one-way hash function MACs, a hash of one key plus a hash of another key plus the message. Yeah. We get the idea. Everyone wants to try and use a hash. The problem with them is that they seem secure, but there's really no proof. And we're sort of skeptical of it. But thankfully, we don't have to figure this out, because let me give you an aside. There is another thing that you can do with Merkle-Damgard hashes, and that is you can do an extra finalization function that is one way. And it only operates on a single block. And I think Bruce Schneier recommends you can just use SHA twice. And the second one basically finalizes the first one so that nobody can go backwards. But it turns out we really don't have to worry about that too much. That's only if you have some legacy system that you can't change. There's something called HMAC. This is a hashed message authentication code. And we've got a, we basically don't even need to look at this too much, because it doesn't make sense even to me why this actually is magic, but it comes with a proof of correctness. So if that makes complete sense to you, congratulations, you're smarter than me. But yeah, there's a proof out there. So this looked like a fail, but it's actually a win. All right. So another thing you can do is you can derive multiple keys from one key. You could seed a computationally strong pseudorandom number generator. But you can also use HMAC to do this. So if you're stuck in some situation where you've agreed on one key and you need two keys, maybe one for authentication, one for encryption, you can actually derive them securely by just HMACing them, using that key S, and HMACing two strings, let's just say 1 and 2, to get your two different keys. And the neat thing is that K1 and K2 here can't be used to attack each other, and they can't be used to attack K because they've gone through the HMAC. So this is just a very simple pseudo-random number generator. You can actually use this as a PRNG if you really want to. It's kind of slow, but it's handy if you're stuck in some legacy framework. So just to show you where this falls in the matrix of cryptography, we've got asymmetric and symmetric, and encryption and integrity. So message authentication codes are sort of the symmetric integrity protection, or you can consider them the symmetric version of, or I'm sorry, or you can consider them the symmetric version of a digital signature, right? So once again, in web apps, everything that you send out comes back to your own server generally, so you don't need asymmetric crypto, with the exception of TLS, of course, but that's all cookbook. So let's get to the good stuff. The WordPress cookie integrity protection. So basically, what they did is they had a separator character, right? And they put a username, separator, expiry time, separator, MAC. And the MAC is computed in an interesting way. The MAC, they computed over the username and the expiry time. Any guesses as to what the flaw is here? It's not trivial to see. The people who wrote it probably didn't get it. You might be guessing that it has something to do with the separator character, and you're probably right. What happens, because they didn't put this delimiter here, somebody actually, they hacked Light Blue Touch Paper, which I think is Ross Anderson's blog. They logged in as a username of admin0, and then they created this forged authenticator. And they basically created a valid authenticator for the user admin0. And the gist of it is that when it was being parsed by PHP, that 0 became part of the expiry time, and it was ignored as a leading 0. So then they were able to use this. Cookie to log in as admin, and it's pretty clever, really, really clever. So basically, they just took the authenticator off of one and put it on a different one, and that was it. And it's a tricky attack, and it's not really easy to tell developers how to fix this. Like you tell a developer, well, you need unambiguous formatting. Well, he thought he had it, right? It works if you have fixed with fields. We need something better, right? We need something, it's not XML and it's not ASN.1 perhaps, yeah? Mm-hmm. Yeah. Yeah, I mean, they had the source code to WordPress. So, yeah. But yeah, and there's an interesting attack, I think it's, or an interesting video, Chris Ng, Cryptography for Pen Testers. If you're interested in doing that, I recommend checking that out on Google Video or YouTube or wherever it is. I've linked to it at the end of my talk, too. So WordPress sort of failed it. No big surprise there, but we might have expected that the crypto worked, at least. So we need unambiguous representations. And that's sort of why we have ASN.1, but that gives anybody a headache to try and like read the ASN1 documentation. It's like, it's just really bizarre, generic terminology, OIDs, and yeah, I shudder. Okay, so someone please solve that problem for me. So don't do this. Don't use electronic code mode. Don't use stream ciphers such as RC4. Don't use MD5 hashes or even SHA-1 these days. Don't reuse keys for different purposes. Like don't use the same key for encryption and for your website or for authentication or whatever. I mean, this just everyone should know this, but it applies to crypto too, not just web passwords. Don't use fixed salts or IVs. Don't roll your own cipher. Don't rely on the secrecy of the system. Sorry. And don't use guessable values as random numbers or as PRNG seeds. And the time your web server started up is not a random value. So keep it as simple as it can be, but no simpler. Understand the cryptographic properties of the tools, and assume the adversary knows all but the keys. And always strive for unambiguity in your plain text and ciphertext blocks. Now, when you're in doubt, these are kind of my recommendations, is that you use AES-256 mode for encryption and CBC. Mode, that is. And unless you're mixing trusted and untrusted data or different data sources, and then you may have to worry about like beast-style attacks. That's sort of a special case that I can't give you really good advice for right now. But if you're doing integrity protection, HMAC SHA-52, or actually now the SHA-3 standards have come out, and so we have a new SHA-3 winner. And so maybe you can use that for your integrity protection as a pseudo-random function there. You can use SHA-512 or the new SHA-3 for your hashing. You can use PBKDF2 for stored passwords or key derivation. And then WRandom on Unix and RTLGenRandom or CryptGenRandom from that on Windows. And that's a mouthful to say. So for further reading, there's a cool thing called the cookie eaters. There's the OWASP 5037, Cryptography for Pen Testers. Steve Weiss from Google has a good talk called Cryptography Theory and Practice. And Nate Lawson has a cool video called Crypto Strikes Back. All right, well, I ended a little early, so. Yes, I don't know how to do that, but as soon as I find out. Oh, okay. Okay, so you're going to do that for me. Thank you. All right.